Hello, friends. Today we are going to talk about convex optimization, and it's going to be clearly explained. This video explains what convex sets and functions are, and how we can generalize both the two definitions. Let's say we are in a large lake, and we wanted to select 2 points at random inside the lake, and connect them with the line. We could do the same for any 2 points and any line connecting them. Notice how, for any 2 points in our lake, the line formed between lies inside the lake. We call this a convex set. Note, we could make the segment go outside the lake, but it would no longer be a straight line segment. To give a more formal definition, a set is convex if for any 2 points inside the set, the line connecting the points exists within the set completely. We can take more shapes and see what happens. We observe that all the segments we can draw are contained within our set, so this is a convex set. We can do the same, but for more intricate sets, and find that some of them are in fact not convex sets. Going back to our original example with the lake, it was nice and easy to visualize, but sometimes we cannot do that. We need some math. Recall that a set is a grouping of plain numbers. They can be finite sets, or they can be infinite sets. Here, the infinite set is represented by 1 over n. Let's define our set as S, and our 2 points as S1 and S2. A set is convex if lambda multiplied by S1 plus the quantity 1 minus lambda multiplied by S2 belongs to our original set S. If this holds for all points we pick in the set is convex. Here, lambda can take any value between 0 and 1 non-inclusive. It's up to us. To understand what the formula is doing, let's take a finite set and select 2 points at random. Here, our set is -3, -2, -1, 0, 1, 2, 3. We select points -2, 1 to test. Plug them into our formula, and pick a suitable lambda. Here we chose 0.9. When we do the math, we get -1.7. We plot the point. If we only tweak lambda and keep our 2 points the same, we start with 0.8, and when we plug that in, we get -1.4. We do the same for lambda equals 0.7, and we get -1.1. And so on. If we keep doing this, at lambda equals 0.1, we get a value of 0.7. We see a pattern. When we pick the random points -2 and 1, we see that when we increase lambda by 1/10 each time, the output continuously slides over the entire interval. All that Matt just said, for 2 points and the line between them, all the points on that line segment should belong in that set. Even though convex sets aren't really used for optimization, we can use them to define convex functions. We take the simplest example, f of x equals x squared. Let's take 2 points at random on the curve, and connect a chord. We say a function is convex if the line is above the function and the curve sags below the line in turn. However, we aren't done. Just like a convex set, this applies for all 2 points on the curve. We have an issue. Visualizing large functions that may not even be in 2 dimensions is hard. We introduce a formula for this. Whoa, this looks hard. Let's break it down. Let's start with the left-hand side first. On closer inspection, this looks like the convex set formula, just evaluated at our function f. Here, x1 and x2 are any 2 points on the horizontal axis in the domain of f. We pick x1 and x2 as -2 and 1 respectively. Remember, these are just numbers on the x-axis. We pick an intermediate middle value with lambda equals 0.7. Lambda also abides by the same rules as convex sets, 0 and 1 non-inclusive. We call this intermediate value we just picked lambda hat, which is a blend of x1 and x2. When we do the math and plug in 0.7 and our two x's, we get a value of -1.1. When we evaluate our function, we get 1.21, which is the entire left-hand side. If we go to the right-hand side, this is the exact same thing, but this time on the vertical axis. Here, f of x1 and f of x2 are any 2 points on the vertical axis. If we plug in the points we just used, which are -2 and 1, we get outputs 4 and 1 respectively. We smush our points to one dimension because we no longer need the horizontal axis. We can do this because of the intermediate value theorem, but that's unimportant. Our lambda equals 0.7 stays the exact same, and when we plug in the math, we get 3.1. This is the entire right-hand side. When we compare both, the inequality holds. However, this is not enough. A function is convex if the math holds for all values of x1 and x2, as well as all suitable lambdas. We can make it even simpler. A convex function has the same local and global minimums. This means any algorithm that uses minimums will love convex functions. Hint, hint, gradient descent. If you don't know what a local or global minimum is, no sweat. A local minimum is the lowest point in its own neighborhood. A global minimum is the lowest point in the entire function. If you're standing here, every direction nearby goes up. But this isn't the lowest point. There's a deeper valley over here and we'd never know. A convex function has to have exactly one minimum, and that minimum is the local and global minimum. This function is not convex due to the local minimum, which is not the global minimum. We also see how it fails the 2-point chord test, since the function is above the chord and does not instead sag down. Most functions in the real world, however, are not convex. We take these three functions. We can see how they all fail the line test. Function 1 is not convex since there are multiple global minimums. Function 2 is not convex since there is no defined finite minimum of the function. Function 3 is not convex since it has no minimums, plus it is simply facing downward, so it is concave instead. We can't always tell just by looking, especially for functions we can't easily draw. We need a test. Enter the second derivative. We say f is convex if the second derivative of f is greater than or equal to 0 for all x in its domain. The second derivative measures curvature. Positive curvature everywhere means the curve always bends upward, like a bowl. Suppose we have this wiggly function which we just looked at. We know it's non-convex, but let's prove it here. The function actually exists as y equals x to the fourth minus 2x squared. Let's take the first derivative. We get 4x cubed minus 4x. The first derivative finds maximums or minimums, so we don't know which one. So we have to take the second derivative, which we get 12x squared minus 4. Now we check, is 12x squared minus 4 greater than or equal to 0 for all x? We can do this by setting the equation to 0 and solving for x, where we end up with plus or minus 0.577. We can take a sign test and find that the function is negative between negative 0.577 and positive 0.577. This would have been obvious since we had a negative intercept, so we already knew the function was below the x-axis at that region. This means the second derivative of f is less than or 0 somewhere. So y equals x to the fourth minus 2x squared is not convex. If we take a obviously convex function y equals x squared and do the math, we'll get our second derivative as 2. 2 is greater than or 0 always for all x, so the whole function is strictly convex. The end.